Hi everyone, this is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So we are discussing about solid mechanics and material subject. So in this subject, in previous session, already we have discussed about Euler's column theory. And in this theory, actually there are different conditions are there, and conditions of column. So already we have discussed about first and condition, and then second and third and fourth conditions are pending. We will see in this session. So the end conditions of column, so depends upon the Euler's equation, that end conditions of the column. So in today's session, we will recall the Euler's column theory, and then again we will see the derivation part of this end conditions of columns. So at the end of the course, the student should be able to analyze the Euler's column theory and deformation of columns and struts. So this is the outcome of this topic. So first of all, introduction. The Euler's column theory: a structural member subjected to an axial compressive force is called a strut. So already we have discussed in the previous session. Once again, I recall these columns and strut definitions. As for definition, a strut may be horizontal, inclined, or even vertical. So examples: connecting rod, piston rod, etc. So the structural member subjected to an axial compressive force is called a strut, and but a vertical strut used in buildings or frames is called a column. So the long, short columns structures are called as strut, and the long vertical strut is called a column. So example: failure between roof and floor. So what are the failures of the column and struts? So it has been observed that when a column or strut is subjected to some compressive force, then the compressive stress induced, that is sigma is equal to load per area. So whenever the column or a strut is subjected to compressive force, so there will be a stress induced in the column. So that stress is called compressive stress, where P is compressive force and A is cross-sectional area of the column. If the force or load is gradually increased, the column will reach a stage. That stage is called ultimate crushing stage. So that is called as ultimate crushing stress. So beyond this stage, the column will fail by crushing. So that load, the corresponding to the crushing stress, is called crushing load. That the corresponding stress is called crushing stress, and the load is called crushing load, and also that load is called as a crippling load and a buckling load. The compression member does not fail entirely by crushing, but also by bending. So that is buckling. This happens in the case of long columns. So all the short columns fail due to their crushing. But if a long column is subject to a compressive load, it is subject to a compressive stress. See, due to the corresponding crushing stress, the crushing load will be obtained. But the compression member does not fail due to this crushing load, but also by bending load, the structure will be fail. So that is called as buckling load and crippling load or critical load. So long columns are subjected to compressive load, it is subjected to compressive stress. So according to the Eulers column theory, the first national rational attempt to study the stability of long columns was made by Mr. Euler. So he derived an equation for the buckling load of long columns based on the bending stress. So he has derived the buckling load equation. But this equation, when while deriving the equation, the effect of direct stress is neglected. This may be justified with the statement that the direct stress induced in a long column is negligible as compared to the bending stress. So direct stress is neglected and justified with the statement that the direct stress induced in a long column is negligible. So the assumptions in the Euler's column theory, the following simplifying assumptions are made in the Euler's column theory. So initially, the column is perfectly straight and the load applied is truly axial. The cross section of the column is uniform throughout its length. The column material is perfectly elastic, homogeneous, and isotropic, and thus obeys Hooke's law. So assumptions in the Euler's column theory, the initially the column is perfectly straight line. That is straight shape. There is no bending. The load also applied truly axial load only. The load passing through its axis of the structure. And also the cross section of the column is uniform. There is no deviation throughout its length. And also it obeys Hooke's law, and the material is elastic and homogeneous and isotropic. So other assumptions are the length of the column is very large as compared to its cross-sectional dimensions. The shortening of column due to direct compression being very small is neglected. The failure of a column occurs due to buckling alone. So these are the assumptions made while deriving this Euler's column theory. And sign conventions also important. Once again, you will see the sign convention. So there are different signs used for the bending of columns in different books, but we shall follow the following sign convention, which are commonly used and internationally recognized. The positive is convexity and concavity is negative, as shown in the figure. So now, types of end conditions. In actual practice, there are a number of end conditions for columns, but we shall study the Euler's column theory on the following four types of end conditions. So these are the important from the subject point of view. So both ends hinged, the first condition. Second condition is one end is fixed and another end is free. Third one is both ends fixed. Fourth is one end is fixed and other end is hinged. So based on these end conditions, we will have to derive the Euler's column theory equation to avoid the buckling. So both ends hinged. The condition is already we have discussed in the previous session. And remaining, we will see in this session, one end is fixed and other end is free. The second one and the third and fourth we will discuss. So coming to the second one, columns with one end fixed and other end is free. So in this, consider a column AB of length L fixed at A and free at B and carrying a critical load at B. So as a result of loading, let the beam deflect into curved from AX1 B1. I will show you the diagram. Thus that free end B deflects through A and occupies a new position B1 as shown in figure. So now consider any section X at a distance X from A. So this is the end condition of the column diagram. One end fixed and other end is free. So this is fixed and free. Free end and fixed end. So length of the column is L. So whenever this subjected to axial load, it bends, deflect as shown in figure. See, the deflect into curved form AX1 B1, so that free end B deflects through a end and occupies a new position B1, AX1 B1. See, AX1 and B1. So previously, before deflecting AXB, and after deflecting, after applying load, the deformation will be AX1B. So let assume the P is a critical load on the column. So deflection of the column at X. So what is the moment due to the critical load? What is the deflection at X is a cross section? X1, the moment due to the critical load, moment is equal to positive sign P into A minus Y. So the total distance is A and the deformation is Y. So now the moment due to critical load P multiply with A into A minus Y. So why here plus sign used? Due to the convexity towards initial center line. Already I will show you that diagram. Convexity. The positive sign. Clear? So now write down the equation EA into d square y by dx square. The m is equal to EA into d square by dx square momentum. So according to the bending stress equation. So according to bending stress equation, already you know sigma by y is equal to m by I into E by R. In this, already we have derived this bending stress equation. So now write down the bending moment m equation sigma by y into I. So now the EA into d square by dx square is equal to P into A minus P into Y. So now d square y by dx square plus P by EA into Y is equal to P into A by EA. So the general solution of the above differential equation is y is equal to C1 cos x into square root of P by EI and C2 sine of x into square root of P by EI plus EA. So where the C1 and C2 are the constants of integration. So now you have to find out the constants, this C1 and C2 obtained from the boundary conditions. What are the boundary conditions here? For a fixed end, the deflection and slope is 0. Hence, at a fixed end A, the deflection y is equal to 0 and slope dy by dx is equal to 0. So at the fixed end, there is no deflection. This is free and fixed. So in this, at this stage, A and B, deflection 0 and slope also 0. So hence at A point x is equal to 0 and y is equal to 0, substitute in a previous equation in this equation. So we will get C1 is equal to minus A. From equation 3, the C2 is equal to 0 or is equal to 0. Now we consider C2 to be equal to 0 as also C1 is equal to 0. So it indicates the column has not bent at all, or bending of the column will 0, but it's not true. Already we have derived in first condition. Both ends fixed. So at A point x is equal to 0, dy by dx is equal to 0, differentiating with respect to x, we get in first equation, we will get the difference equation C1 into minus C1 square root of P by EI into sine into x into square root of P by EI plus C2 square root of P by EI into cos x into square root of P by EI. So substituting x is equal to 0, dy by dx is equal to 0 in the above equation. So after simplification, substitute x is equal to 0 and dy by dx is equal to 0 in this equation. You will get C2 square root of P by EI is equal to 0. Therefore, the C2 is square root of P by EI is equal to 0. Since the load P is not equal to 0, it is obvious that C2 is equal to 0. Now substituting the value C1 is equal to minus A. Already we know C2 is equal to 0. Now these two values substitute in a first equation. So finally we will get cos L into square root of P by EI is equal to 0. So now here for values L into square root of P by EI is equal to cos 90, cos 0, pi by 2 and 3 by 2 and 5 by 2. So C1 is equal to minus A and C2 is equal to 0. Substitute in this equation. So now taking the least significant value, that is L into square root of P by EI is equal to pi by 2. So this is the least significant value. Here L into P by EI is equal to cos inverse 0. So that is 90 pi by 2. So now squaring on both sides, L square into P by EI is equal to pi square by 4. So now calculate P is equal to pi square EI by 4L. So this is the the load, buckling load on the column when the end conditions are one end is fixed, other end is free. The equation, Eulers equation is pi square EI by 4L square. So next third one is columns with both ends fixed. In previous case only one end is fixed and another end is free. But in this condition, the columns with both ends are fixed. So again, in the same manner, you have to derive the equation. See, in this diagram figure shown, both ends are fixed. Initially, A, X, B. After bending this one, A, X1 and B. And movements M0 at both ends. So the structure, the column bends like this. So one and length we fix length L, the column AB of length L fixed at both of its ends, A and B, carrying a critical load critical load at B. As a result of loading, that the column deflects as shown in figure. So now assume P is the critical load on the column and Y is the deflection of the column at X. Consider any section X at a distance X from A. A little consideration will show that since both the ends of the beam AB are fixed, it is carrying a load. Therefore, there will be some fixed end movements at A and B. So both ends are fixed, so that the movements occurred at A and B. So let M naught is fixed end movements at A and B. The moment due to the critical load P is M is equal to minus P into Y. So why it is negative? This is due to the concavity shape negative. So now write down the equation A into d square y by dx square is equal to M naught minus P into Y. So now d square y by dx square plus P by A into Y is equal to M naught by E. So the general solution of the above differential equation, Y is equal to C1 cos of X into square root of P by EI plus C2 into sine X into square root of P by EI plus M naught by P, where C1 and C2 are the constants of integration. The values of constants obtained from the boundary conditions. So already we have calculated in a previous case. Here also same procedure need to apply. So dy by dx is equal to differentiate the above equation C1 minus C1 square root of P by EI into sine X into square root of P by EI and plus C2 into square root of P by EI into cos X into square root of P by EI. So substituting X is equal to 0 and dy by dx is equal to 0 in above equation. Why? Because both ends are fixed. At their fixed end, there is no slope and the x is equal to there is no slope and deflection. X is equal to 0. Since the load P can't be equal to 0, so the obvious C2 is equal to 0. Now substituting the value C1 is equal to minus M naught by P and C2 is equal to 0. In equation 1, C1 is equal to M naught by P and C2 is equal to 0. So substituting X is equal to 0 and dy by dx is equal to 0 in the above equation, we will get 0 is equal to C2 into square root of P by A. From the equation 3, the C2 is equal to 0 of square root of P by A is equal to 0. So now you can write down the equation y is equal to minus M naught by P cos X into square root of P by A plus M naught by P. At B, X is equal to L, Y is equal to 0. Therefore, 0 is equal to M naught by P into 1 minus cos to L into square root of P by EA. Cos L into square root of P by EA is equal to 1. So L into square root of P by EA is equal to 0. Cos was 1. Cos 0 is 1. So that 2 pi and 4 pi and here also take least significant value. That is L into square root of P by EA. So again here squaring on both sides. Sorry, L square into P by EA is equal to 4 pi square. So P is equal to 4 pi square EI by L square. So this is the final equation when the both ends are fixed. In previous case, the both ends are, one end is fixed and other end is free. The equation is 5 square into EI by 4L square. But in this, both ends are fixed. 4 5 square EI by L square. So this is the difference between these two conditions. So these are the references I have taken. S. Ramavrutam. Title of the book is 10th of Material. Publishers Dhanpati Rai Publishing Company and R.K. Bansal. Textbook of 10th of Materials. And R.S. Kurmi and Gupta. So take any one reference and for other more information. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.